Okay guys, we are going to review what we've learned so far on action potentials and graded potentials. One thing we'll need to be able to do is to interpret a membrane potential graph. And I'm going to give a bunch of hints throughout these two slides. There's really only two slides as to what kinds of questions I might ask you about this stuff. Okay, so the first thing I'd want you to know for sure would be the basic situation that we're dealing with when it comes to the abundance of ions on the inside and outside of any particular neuron. Okay, and so we've seen this a bunch of times before. We've got our standard cell, there's our nucleus. We've got our sodium-potassium pumps that are pumping more sodium out and more potassium in all the time. And we also have differences in calcium and chloride across the membrane, where there's more of both of those outside the cell. Okay, so there's more of sodium, calcium, and chloride outside the cell, more potassium inside. When we take it all into account, we have an electrical gradient as well, where it's more positive outside and more negative inside. That is, in fact, our resting membrane potential, that difference, right? And what we do is we represent these on a graph, right? So if the cell is negative, we say the cell has a certain negativity to it. And in fact, the standard neuron is going to have a negative 70 millivolt charge to it. Okay, that's the membrane potential of that particular cell. Now we know there's some other important numbers in addition to the resting membrane potential, which is a situation where the cell is polarized, right? It starts out this way. We also have a threshold, which is negative 55 millivolts, which will become more important when we talk a little bit later about graded potentials and forming action potentials. But if we were to just take any random location and say, okay, down here on this cell in the bottom left, we've got, I'm going to draw a little dash across here, we've got an action potential that happens to be in this particular location on this nerve fiber. In this case, it looks like an axon. Okay, what can we say about that? Well, what we can say about that, in that location, what's happening is there are channels opening for sodium. Okay, the sodium comes rushing into the cell. We can show that on the graph just like this, right? We'd say that it is depolarized the cell. We've had the sodium influx. We've gone from more positive outside to zero and then flipped the charges. Okay, so now it's more positive inside the cell, which is why we're up here now above zero. Okay. Next, what happens is potassium flushes out of the cell, right? So we have in green our potassium, we have a repolarization as now we flip the charges, now we flip them back, right? Potassium is going to leave, which is a positive item as well, okay? And it actually kind of undershoots our target, and so you have a little bit of a hyperpolarization in the process, okay? Basically, up in our graph, we could say the potassium was going this way. Now, at this point, that's our action potential, right? And at this point, all the sodium has now gone into the cell and all the potassium has gone out. It all needs to be pumped back using our sodium-potassium pumps. So this brown line here, I've indicated a region, a span of time during which the sodium is pumped out as it should be and potassium is pumped in as it should be, and that's all represented here, of course, with our sodium-potassium pump. Okay, now that also has a name. Okay, sometimes you can take the very beginning, so way over here where the sodium started making the line go up, to all the way over here where we're done pumping all of the ions back where they belong. And at this point, we're ready for the new action potential. Or you could just take this region from where we had the end of our hyperpolarization to the point where we're ready again for another action potential. And these are forms of what we call refractory periods. Okay? Now, what I'd want you to come away with is the basic idea that a refractory period is a time we have to wait before the next action potential can form. okay? But like I say, if we pick any point and say that there's a nerve fiber, there's an action potential in this location, this is what it's going to look like, the reason it's going to happen is because sodium goes in, potassium goes out, pumps fix everything, we're ready to go again. Now what we learned about this action potential, or we sometimes call it an impulse, is that sometimes they can move super fast because there's myelin sheaths there, or because it's warm, or because there's some chemical there that allows that doesn't allow the sodium ion channels to open very readily, or it allows them to open very readily, right? And that's going to impact the speed at which this forms again and again on that nerve fiber. Okay, so that's just kind of in a nutshell what we know about an action potential. Now, let's turn our attention to what happens between two cells. Not when we're just following it down nerve fibers, but we're looking at a synapse now. Okay, so now, let's see. Now we're going to look at a cell, a presynaptic cell, and it is releasing some neurotransmitters, and we're going to see the effects of that presynaptic cell on a postsynaptic cell. Okay? So what we're doing here is now we have a graph. It's again a membrane potential graph. Again, we're measuring things in millivolts, right? We are, in fact, in this case, measuring the millivolts of the postsynaptic cell. I'm going to mark it with an X, okay? This is the cell that we're measuring now on this graph. And, of course, we're starting at -70 as we'd expect, okay? Now, we're going to say that there is an action potential. I'm going to draw a little dash here on our presynaptic cell axon here. There's an action potential right here, and it is moving down. And then when it gets to the end of this axon, all sorts of things are going to happen, right? Calcium's going to rush in, neurotransmitters are going to be released. They're going to come out in this region. Let's put a few little dark dots here, okay? And they're going to bind to a receptor on the postsynaptic cell. Now what that postsynaptic cell does in response to that neurotransmitter all depends. It depends on which ion is allowed to pass at this location. It's not just going to be sodium. It could be sodium, calcium, chloride, or potassium. Again, we have, just to remind us, up in the corner here, all the various possibilities that could take place. Let's say that this neurotransmitter allows sodium to pass. Well, sodium's going to go in, the line's going to go up, right? It's going to have a tendency to move that line upwards. But let's just say there's just one release of neurotransmitter. One action potential reaches the end of that axon, one poof of neurotransmitter, certain number of them are going to bind and allow for, let's say, sodium to pass. Well, if sodium goes in, we know the line's going to go up, but just because there's only one release, we might see that it goes up, comes right back down, never gets to threshold. Well, if we don't get to threshold, we're not going to form a new action potential. If we don't form a new action potential on this postsynaptic cell, it's not going to have an impulse move down its axon, okay? This, in this particular case, would be a graded potential. It could be that the neurotransmitter allows sodium to go in, or it could be that it allows calcium to go in, and we could still get the same result. Now, this is a depolarization of the cell, okay? This is a depolarization because the line goes up. It doesn't have to totally flip the charges to call it a depolarization, okay? But because it depolarized and went up, we would say that it is excited to a degree. Excitatory postsynaptic potential. So, looking forward on a test, right? If I say there's a graded potential and this is what it looks like, right? The line went up. You know immediately a few things. You know it was either sodium or calcium involved, and you know that it was exciting the cell. I could give you any one of these pieces of information, and you could give me the rest. Okay? If I tell you that calcium was allowed to pass through the channels at a synapse, you should be able to tell me that it will excite the cell and depolarize the cell. If I tell you that a neurotransmitter is excitatory, it's going to excite the next cell, you can tell me a few things. It's going to depolarize the next cell, and it could be sodium or calcium involved, right? So I give you one piece of information, you can give me the rest, all right? All right, now let's say that we have a release of a different neurotransmitter here. Let's say the neurotransmitter that's released here now is actually allowing chloride to pass. Well, we know what chloride will do, right? Chloride would, given a chance, it would go down its gradient, go from outside the cell to inside the cell. So we'd have chloride do this, right? It would go into the cell. But chloride is a negatively charged item. It's already negatively charged inside the cell, right? And positively charged outside the cell. But now it's going to be even more negative. So as you add negatives to the inside, it's going to get more negative, and the outside is going to get more positive. You're going to have a bigger difference across the membrane. It's not like we're making the two sides more equal. We're going to make them less equal. We're going to make the line go down. Okay, so we're going to see this line go down, and we're never going to get to threshold going that direction. We immediately know, having seen this, that this is a hyperpolarization. Okay? We can immediately say that. But we can also say that it's not an action potential, it's simply a graded potential that went the other way. Right? We can say it's a graded potential, chloride was allowed to pass, or potassium was allowed to pass, and it was inhibitory on that cell. Again, I should be able to give you any one of these pieces of information, you give me the other. If I tell you the release of a neurotransmitter hyperpolarized the cell, you can tell me it's either chloride, potassium passing, it's going to be a graded potential automatically because you're going the wrong way, never going to get to the threshold, and it's going to be inhibitory on the cell. If I tell you channels were open for potassium by a neurotransmitter, you could tell me you're going to have graded potentials that are inhibitory, hyperpolarizing the cell, going the wrong direction. Okay? Now let's say, let's wipe this clean for now, okay? Let's say now that we have an excitatory cell. I'll tell you right out of the box here, we have an excitatory cell. The presynaptic cell is going to excite. Okay? So that's a big clue. We immediately know a few things about this. It's going to have sodium or calcium passing through the membrane. You're going to have a depolarization. So here we have our neurotransmitters. It binds. And let's say for argument's sake, sodium's the thing that goes in. Okay. Now we know, let's say if just one release of sodium occurs, let's say that doesn't get to threshold. But let's say that we don't just have one release. Let's say we have one action potential that's going to reach the end of this axon and release a few neurotransmitters. But then right behind it, we have another action potential moving that's going to allow a few more neurotransmitters to be released and to bind the receptors on the next cell. Well, that'll allow even more sodium to go into the postsynaptic cell. This is kind of what we're going to see. We have an excitation. That first excitation is going to have the line go up a little bit. Then we're going to have our methods by which that neurotransmitter is going to disappear, right? Diffusion, degradation by enzymes, and reuptake. But then before they can all go away, we had another release of neurotransmitter. Another action potential reached the end of that axon. And that, lo and behold, gets us to threshold. If we get to threshold, there's going to be an action potential, right? In this particular case, this is E1, so we'll just give it a number, okay? This excitatory presynaptic cell number 1 got us to threshold. By piggybacking to get us to threshold, we call that temporal summation, okay? And in fact, we do get an action potential in that particular case. All right, Let's wipe the slate and let's do one more example. Let's say we have another presynaptic cell, okay? And we have E1. This is going to be an excitatory cell. And we have E2 that is also going to excite the postsynaptic cell. Let's just say, for argument's sake, the action potentials are moving down and they're going to reach the end of the axons at the same time on both of these cells. Well, then you would have a greater amount of neurotransmitters affecting the postsynaptic cell, a greater amount binding the receptors on the postsynaptic cell membrane, and you would have a greater amount of, let's say, sodium in this case, but it could be calcium, passing into that postsynaptic cell. We would say that there's E1 and E2, a simultaneous stimulation of that postsynaptic cell, and we see something possibly like this, where we might get up to this point with the initial amount of neurotransmitter and sodium entering the cell, but then at the same time you had even more neurotransmitters released, so it gets us the threshold. Well, in this case, there's really kind of two different areas, two different spots or spaces, right? You might think of it as two different spaces on the postsynaptic cell where the cell is responding. Spatial summation, okay? Now, what's that going to cause? Well, if it gets the threshold like it did here, well, we know what's going to happen. It's going to go, it's off to the races again, right? It's going to have another action potential, right? Now, this is not always the case. Let's say you had an inhibitory cell on one and an excitatory cell on the other. And let's say that an equal amount of chloride entered the cell on one side and as did sodium on the other side. Well, they just cancel each other out, right? One is negative and the other one's positive. So there's no guarantee that spatial summation would end in an action potential. And keep in mind, they could be both inhibitory, in which case you just go down and down, right? Never get the threshold. All right, so I just wanted to kind of put all this in a nutshell, show you a graph. You should be able to interpret a graph like this. I give you an ion, you tell me if it's going to excite or depolarize the cell. I give you that it's going to inhibit the cell. You give me ions that are capable of that, and stuff like that, okay? All right, I think I'll leave that for now, guys, and we will talk about a range of different neurotransmitters. We'll talk about dopamine. We'll talk about cocaine and what it does. We'll talk about heroin. There's a big opiate epidemic right now, a big problem with that. So we'll talk about that as well. We'll talk about what some of these different natural neurotransmitters in our brain are doing. It's not just acetylcholine. We've got a whole bunch. Okay, there are books on these things. All right, so we'll leave it at that, and I'll see you next time.